Welcome to lecture number 5, ladies and gentlemen. We'll be looking at pulse modulation. This is in a course EEE 4682 Communication Systems. The presentation outline will look as follows. I'll talk about the brief introduction about pulse modulation, then we'll look at the 3 major types of pulse modulation. We have pulse amplitude modulation, pulse duration modulation, pulse position modulation, look at the comparison, and then we'll also talk about duty cycle before I give the tutorial. Now, pulse modulation involves modulation of analog signals, and these analog signals are such that the carrier is in pulse form, whereas the baseband signal could be sinusoidal or cosinusoidal. There are 3 common types of pulse modulation. We have pulse amplitude modulation, pulse width modulation, and pulse position modulation. Pulse amplitude modulation, like I said, is an analog modulating scheme in which the amplitude of a pulse carrier is varied in accordance with the baseband signal message signal. The pulse amplitude modulated signal will follow the amplitude of the original signal. That is in a case for a natural palm, or you also have another type which is flat palm, which does not necessarily follow the exact position of the message signal. To illustrate this, I have a block diagram here. You notice that in this block diagram, I have a sine wave generator generating the message signal, and then I have a square wave generator where you are generating the pulse carrier. And when the 2 meet in the modulator, you get a palm output. That modulator consists of comparator, op-amps, a combination of op-amps, sump and hold circuits, basically to generate a pulse amplitude modulation circuit output. The circuit below here illustrates further. You will have the message signal, which is in sinusoidal form, analog in nature. The pulse carrier, also analog in nature. When the 2 meet in the modulator, you get the palm signal as illustrated on the output after the chopper. The diagram below just shows the details of the sump and hold circuit and the details of the chopper to generate basically a palm signal. Now, the pulse amplitude modulation in terms of a waveform can also be illustrated, whereby you have the first waveform here generating, giving us a modulating signal, and then the second waveform giving the carrier pulse trend. And when the 2 meet in the modulator, you will notice for natural palm, this follows the shape of the modulating signal, and the amplitude of the carrier will be varying in accordance with the modulating signal. You'll notice here that the frequency of the carrier remains the same. What is changing basically is the amplitude of the pulse trend or carrier signal. Now, pulse amplitude modulation has one major weakness, and this is that it has higher noise, and this noise comes from the fact that the palm signal will have varying amplitude, and this noise is usually very difficult to eliminate. The other weakness also is that the transmission power will vary, again due to variation in amplitude, and because of this circuit is seldom used, and so emanating from these weaknesses of the palm, we can now look at other pulse modulation schemes such as pulse width modulation, also called pulse duration modulation. It's also analog modulating scheme in which the duration or width of the pulse carrier is varied in accordance with the message signal. So you keep the amplitude constant, but you are varying the width of the carrier. So the width of this carrier will be varied while the amplitude of the signal remains constant. And to maintain the amplitude at constant level, normally we use what are known as amplitude limiters or clip and limiter circuit, which we studied in electronics. And so this circuit clips off the amplitude to desired level, and hence the noise is limited. And it is because of this ability to maintain a constant amplitude, as you will see later, this is actually one major advantage of pulse width modulation. And in terms of a block diagram, pulse width modulation can be illustrated as shown in this block diagram here. And what you notice is that again you have the message signal, which could be sinusoidal, cosinusoidal. These are being combined in the pulse width modulator with the carrier signal, which is basically a pulse signal. And this pulse signal there, when they are combined, a pulse width modulator, you get a pulse width modulated output. In terms of the waveform, you can actually see here that with pulse width modulation, like I said, the amplitude is kept constant. What you are varying is the width of the carrier. And the three possible outputs can be generated for a pulse width modulation. When you consider, what is known as the rising edge, rising or leading edge of the carrier, you get the first pulse width output as given in A, whereby you keep the with the leading edge. What will be varying will be the trailing edge. Then the second possible output is where you are basically, considering the falling edge of the carrier. This is the falling edge, and this will give a corresponding, output whereby you have a falling edge or tail edge, and then what will be varying will be the leading edges of the carrier. Then the third possible output you can get is where you consider the center of the carrier, okay? So basically you keep the center of the carrier constant as shown in this part, but what you're varying are the leading edge and trailing edge of your carrier. So you basically, and what is also of importance to mention here, in each of these, whether leading edge, falling edge, or center of the modulating signal, is to notice that when the signal is positive or for higher values of the carrier, then the signal, the width of the pulse width signal increases, whereas for the minimum values, the width of these, basically will also be reducing. So depending on the shape and the size of the modulating signal, the output will vary accordingly. Now, so like I said, pulse width modulation, there are three variations of pulse width, depending on whether it's the leading edge. Under the leading edge, the pulse is being kept constant, while the trailing edge varies according to the message signal. And the trailing edge of the pulse being constant, the leading edge varies according to the message signal, while for the center of the pulse being constant, the leading edge and the trailing edge will vary according to the message signal. In terms of advantages and disadvantages, With the pulse width modulation, noise is relatively low because the amplitude is kept constant, and also transmitted power will vary due to the variation of the width of the modulated signal. So the width is basically where will contribute to transmitted power. The third type of pulse modulation is what is known as the pulse position modulation. It's also analog in nature, whereby the amplitude and width of the pulses are kept constant. But what you are varying is basically the position of each pulse of the carrier in accordance with the message signal. The transmitters to send synchronization pulses to keep the transmitter and receiver in synchronism. And these sync pulses would normally help in maintaining the position of the pulse. And then in terms of the block diagram, you have the sine wave generator, just like we had in pulse width modulation. And you have the ramp generator, basically to generate a carrier. And the two are put in a pulse position modulator to generate the pulse width modulation, which is the first output here. And you notice that with this pulse width modulation, when we pass it via the monostable circuit, then you're going to get what is known as a pulse position modulator. So basically with pulse position modulation, all you do is get the output of the pulse width modulation, and you pass it through the monostable circuit. So it's basically an improvement of the pulse width modulation circuit. And the waveform here illustrates the pulse position modulation. And as you can see, the first, when you combine the modulating signal, which is given by the first waveform, with the carrier, which is the second waveform from the top, then what you're going to get is basically the pulse width modulation, which is this one here. Then that pulse width modulation, all you do is to get the trailing edge of each of the pulse modulation and then generate a pulse. At every trailing edge, it will constitute the starting position of the pulse position modulating signal. So the last waveform here basically giving the output of the pulse position signal. Now, in terms of advantages and disadvantages of pulse position modulation, one of the advantage of it is that due to the constant amplitude and width, the power handled is usually constant, and also noise interference is low due to constant amplitude. It has one major disadvantage, which is that the synchronization between the transmitter and receiver is a must, and this basically makes it a bit more undesirable. Let's now compare the three in terms of amplitude. With palm, it is the amplitude that you are varying. You keep the frequency constant. With pulse width, you are basically varying the width while keeping the amplitude constant. Same with pulse position modulation. You basically vary the position, keeping the amplitude and the width constant. In terms of bandwidth, with pulse amplitude modulation, bandwidth depends on the width of the pulse, whereas in pulse width modulation, bandwidth depends on the rise time of the pulse. This is also similar to pulse position modulation. In terms of transmitted power with palm, due to the variation in the amplitude, the transmitted power also varies. But with pulse width modulation, you have a case due to the variation of the width of the pulse, the transmitted power also varies. However, in pulse position modulation, power transmitted is constant because the width and the amplitude of the pulse is kept constant. In terms of system complexity, palm is quite high, whereas pulse width modulation and pulse position modulation, they are of low complexity. In terms of noise, noise interference is high in palm, but it's much lower in pulse width modulation and pulse position modulation. Then you can also liken each of these three to what we studied earlier with the amplitude modulation, which is similar to palm, frequency modulation similar to pulse width modulation, and pulse position modulation is similar to phase modulation. Next, I want us to talk about duty cycle. By definition, duty cycle is a measure of the time the modulated signal is in its high state, basically the on state. It is generally recorded as a percentage of the signal period where the signal is considered on. So if you look at this signal here, we can actually calculate the duty cycle if we know the on period, and if we also know the off period, which is those points. Given that this signal will have a period from this point up to that point, therefore mathematically we can actually calculate the duty cycle as shown in the next slide. And duty cycle in this case will be calculated as the on time, the time the pulse is on, divided by the period, the entire period, multiplied by 100, that is the duty cycle. You can also calculate the average value of the signal voltage here, where this is the VL is the lowest voltage, normally taken as 0. VH is the maximum voltage there. So if I know the lowest voltage and the maximum voltage, I also know the duty cycle, then I can calculate the average voltage as given by basically this equation. Okay, so this has been some of the references used, and the tutorial has been given as shown here. So this marks the end of our presentation.